Okay, if you want to find a critical point, you want to find a derivative and you want to set it equal to 0. So if I want to find this derivative, the x is going to go away and the cosine goes the what? Negative. Cosine goes the negative sign, but we already have a negative in here, so my derivative f prime of x would be equal to negative root 2 over 2, and cosine goes the negative sign, so I'm going to double negative this, and that's going to be plus sine x. When I want a critical point, it means I want to set this equal to 0. So if I set this equal to 0, 0 is equal to negative root 2 over 2 plus sine x. To solve this, you want to take the root 2 over 2 over. So in reality, sine x is equal to root 2 over 2. And then when you solve this, you're just asking yourself where on the unit circle is sine equal to positive root 2 over 2. And in this case, that would happen if x is equal to pi over 4 and also at x is equal to 3 pi over 4. So a critical point, I mean, we found them, but what a critical point is, a critical point is where the derivative is 0. So if you're looking at something that looks like this, even though we don't know what these are, if the derivative is 0, that means I have a horizontal tangent. So a critical point is where this thing turns. So it's the same thing as saying a relative max or a relative min, and then we get into more depth with that in a little bit with the first derivative test. But as far as this question asked, it was just asking where are the critical points, and you find a critical point by taking the derivative and setting it equal to 0. Okay, the second one asks us to find absolute extrema. Absolute extrema is when you want to plug in the endpoints as well as the critical points to the original. So let's make a list here actually while we're doing this problem. If I want absolute extrema, I could also want intervals of increase and decrease, relative max, min, or I could ask for concavity or points of inflection. So here's my three big things, right? So if it's absolute extrema, you're taking the endpoints and you're taking the critical points. So you have to know how to find the critical points in the last example. But you're taking the endpoints and you're taking the critical points and you're putting them into the original equation. And that's when we made our box and we said we have x values, we have y values. Biggest y value is your absolute max, smallest y value is your absolute min. When it's asking for an interval of increase or decrease or a relative max or a min, that is your first derivative test. And when it's asking for concavity or points of inflection, that's the second derivative test. So we'll go back through all of these different types of problems as we keep going. So this first one here that we just looked at was absolute extrema, and that's when I want to take my endpoints and my critical points and test them into the original. So the problem we just had was find the absolute extrema for y is equal to cosine x from 0 to 2 pi. So I want to make a chart. There's my x. There's my f of x. So if I look at 0 and 2 pi, these are my endpoints. That's where I want to start. I plug in 0. I plug in 2 pi. And again, this is all about the original in this one. So if I plug in 0 into the original, cosine at 0 is 1. If I go to 2 pi, it's the same spot. Cosine at 2 pi, also 1. So I want to do the endpoints, and I want to do the critical points. So to do the critical points, I say y prime is equal to...
Please pardon the interruption. Isabel Fry, please report to room B131. Isabel Fry, please report to room B131. Thank you.
All right, continuing. So we want to find y prime, and y prime would be equal to, cosine would go to negative sine x. So again, from that last example, to find a critical point, you find the derivative, which we have, and we set it equal to 0. How do I solve this? I could start by dividing both sides by -1. So sine is equal to 0. So solving a trig equation, I'm saying, so where is sine equal to 0 on this interval? So it really happens in two spots, right? Sine is going to be 0 at pi and 2 pi, but 2 pi is already a part of that interval. So the spot I'm interested in is the one in the middle. So at pi, I have a critical point. And again, I'm testing these all in the original. for an absolute extrema. So I take that pi into the original. What do we know? Cosine of pi, that's -1. So here's all my information in the chart. And according to this, my highest y values happen twice. My lowest y value happens once. So I have absolute maxes at 0 and 2 pi. And I have an absolute min at pi. Now we can cheat a little bit on this one because we know what cosine x looks like, or we should know what cosine x looks like. On the test or an AP exam, you would not know what it looks like. They wouldn't give you one at easy. But what does cosine x look like? That is the graph right there, right? From 0 to 2 pi. Here's pi in the middle at -1 and 1. So here's the actual graph you were looking at to begin with, right? So based on our answers, we said there was a max at 0 and 2 pi, which is exactly what you see. At 0 and 2 pi, those are your maxes. And at pi, here's your min right down there. So again, when you're doing absolute extrema, you want to take the endpoints into the original. You want to find a critical point, which is the derivative set to 0, and also plug that back into the original. We put our information here on a table. Highest point or points, if you have a tie, is your max, and the lowest one is your min. Okay, we're looking at the fourth problem in the packet. This is the one with 5 parts. Part A says to find the critical points. So to find a critical point, we want to find a derivative. We want to set it equal to 0. So my derivative would be 24x to the third minus 12x squared, setting it to 0. I can factor out a 12x squared, and that leaves me 2x minus 1 is equal to 0. I set both things with a variable equal to 0, so the first one gives me 0, and the second one gives me positive 1/2. Those are your critical points. Now for part B, asks for the intervals of increase and decrease. So going back to a second ago, we made this list right here. So the prior problem was the absolute extrema problem. That was endpoints, critical points to the original. When it asks for an interval of increase or decrease, or also a relative max or min, that's the first derivative test. So it's asking for an interval of increase or decrease. First derivative test. How do you do a first derivative test? You want the critical points, which we found in part A, and I put them on a table. So I have 0, and I have 1/2, and I circle them. Those are my critical points. And we test the values around it. So I'm going to test -10. I am going to test +10, and be careful to pick something between 0 and 1/2, so 1/4. And I do not care what the values are here. I just want to know if they are positive or if they are negative. So it's the first derivative test. So these test values are being plugged into the first derivative. So where is my first derivative? It's right there. So if I plug in 10 to the third is 1,000, 24,000, you can stop there. You know it's positive. I plug in -10. -10 to the third's -1,000, -24,000. You know that one's going to be negative. Now the one you have to be careful with is plugging in the 1/4. So let's get some scratch paper here so I don't take up too much room on this one. I want to plug in a 1/4 into this derivative right here. So this is 24 times a 1/4 to the third minus 12 a 1/4 squared. So when you raise a fraction to a power, you're raising the top and the bottom. So a 1/4 to the third, 1 to the third's 1, 4 to the third 64. So this is 24 times a 64th minus 12 times 1/16. This is 24 over 64 minus 12 over 16. Again, we don't care what the answer is. We're just trying to get a sense for the sign of it. So to subtract these, this 16 needs to become a 64, so this would be times 4. So this 12 would be a 48, and 24 minus 48 is going to be a negative 24, but negative is what I'm looking for. So that tells me that that sign in the middle is negative. So in terms of the intervals of increase and decrease, it is decreasing from -infinity to 1/2, or you can write that as -infinity to x to 1/2, and it's increasing from 1/2 to +infinity. If it asked you to justify that, you would just say for the decreasing interval, because that's where f prime of x is less than 0, and for the increase, it's because the derivative f prime of x is greater than 0. So for part C, the relative max and min, you go right back to the first derivative test, which you just did. And now this is where I want to start to sketch in the slopes. So I say a negative slope looks like this, and this is another negative slope, so it looks like that. And the positive slope, it changes directions. So where did these connect at, right? Down there, and we would call that point, it's down at the bottom, so that would be a relative min. So we have a relative min at x equals 1/2. Why? Because f prime of x changes from negative to positive at this critical point. Part D asks for a point of inflection, and Part E asks for a concavity interval. So back again to this list, when it asks for concavity or a point or points of inflection, we're heading to the second derivative test. So if I want to do a second derivative test, I should find a second derivative. My first derivative right here was 24x to the third minus 12x squared. So if I derive that, I would have my second derivative. So f double prime of x is equal to 72x squared minus 24x. And again, we're setting that to 0. So when you're doing a second derivative, these are called points of inflection, whereas a first derivative, they're called critical points. I factor out a 24x, and I am left with x minus 1, about 3x minus 1, sorry. 3x minus 1 gives you points of inflection possibly at 0 and at a third. Now, you're not guaranteed that these are points of inflection until you put them on the table and see if there was a sign change that happened. So in other words, if you put them here and I have 0 and I have a third and I circle them. So I make my test values of negative 10 and 10, and between 0 and a third would be like a fourth. I want to plug all three of these into the second derivative. So if this would go like plus, plus, minus, plus, plus didn't change signs, you wouldn't have a point of inflection. So we want to see what happens. I'm just saying if it didn't, you would not have a point of inflection unless you have a sign change from one to the next. In this one, when we plug in negative 10 to the second derivative, negative 10 squared is 100, so that's 7,200. That one's going to be plus. When I plug in positive 10, same thing, that's going to be plus. And when I plug in a fourth, similar to what happened over here, you got to be careful with the math. A fourth squared is a 16th. You go through and do the math, you discover it's a negative. So in this case, you do have a sign change around the 0 and around the 1/3. So you have 2 points of inflection. You have a point of inflection at 0 and at 1/3. Your justification is why? Because f double prime of x is equal to 0, and also because it changes from positive to negative at 0, and it changes from negative to positive at 1/3. So to justify a point of inflection, you want to talk about something about f double prime of x changing from either plus to minus or minus to plus around the, so now instead of a critical point, it's changing around the, what we're calling a point of inflection. For part E, the concavity interval, that's just asking you to say where is it concave up and concave down. It is concave up from negative infinity to 0, and also from 1/3 to infinity. Why? Because f double prime of x is greater than 0 through those intervals, and it is concave down from 0 to a third. Why? Because f double prime of x is less than 0 over that interval. Okay, the next problem is going to be relating to the mean value theorem. So the easiest way to think about this is we sketch a graph, we sketch some sort of curve here, and we'll say that this is going from A and B here. So this is f of B, and this is f of A. So if I want to talk about its slope, that would be this line right here, which could be called the average rate of change. It could also be called the secant line. So to find this average rate of change, it's subtract the y values. So this line right here would be f of B minus f of A over B minus A. And the mean value theorem says that somewhere, if this thing is continuous and therefore differentiable, somewhere on this thing is a point C such that the slope of its derivative is the same as this green slope, the average slope. So in other words, its tangent slope is going to be the same as that secant slope. So this would be f prime of C being equal to that average slope. So to do one of these problems, you're looking to find the normal slope and set it equal to, or make the tangent slope be the same thing. So if you want it to be the same thing, you're going to find the normal slope and then take a derivative and set it equal to, or force it to be equal to, whatever you just found in the average slope. So if we look at problem 5, it says that f of x is equal to sine x from 0 to pi. The first part says find the average rate of change. An average rate of change where a secant line is just find the normal slope. So these values given, the 0 and the pi, so that's your x value, 0 comma something and pi comma something. To find my somethings, I plug them in. If I plug in 0, sine of 0 is 0. If I plug in pi, sine of pi is also 0. So when I find this slope, 0 minus 0 over pi minus 0 is 0 over pi. The average rate of change is 0. For part B, it says find the point that satisfies, in other words, the x value. I'm looking for the x value that satisfies f prime of C is equal to f of B minus f of A over B minus A. All of that just means find out the x value where the tangent slope is going to be equal to, in this case, 0. So that means I should take the derivative. So the derivative of my function sine goes to cosine, and I want to force it or figure out where that will be equal to 0. So I say, all right, where is cosine going to be equal to 0? And now you'll find two spots for that on the unit circle. It would happen at pi over 2, and it would also happen at 3 pi over 2, but we look up here and the interval given is only from 0 to pi, so I take 3 pi over 2 and we cross that one out and we keep the one that fits the interval of pi over 2. So find the point that satisfies this. So we figured out that at x equals pi over 2, this is going to have the same slope as the average. And then in part C, we want the equation of this tangent line where this all happens. So how do I find the equation of a tangent line? I need a point, I need a tangent slope. Well, I just discovered that the point is going to be at pi over 2, comma, we don't know yet. And all of these things, the average slope is 0, and the mean value theorem says I want the average slope to be equal to the tangent slope. So regardless, I'm wanting a tangent slope, but all of my slopes in this problem are going to be 0. So now I just need to figure out this y value. So I go back to my original problem and I say, well, at pi over 2, what do we got? Sine of pi over 2 is 1. So I want y minus 1 is equal to my slope, x minus pi over 2. Y minus 1 is equal to 0. Y is equal to 1 is the equation of the tangent line. Now, again, we can kind of cheat in this problem because we know what sine x looks like, or we should. So if we take a second here and graph this, they told us we had sine x, but only from 0 to pi. So here's how sine starts. It's, am I still recording? Why did the screen go blank? It's still recording, but the screen went off. I don't know why. I'm going to keep talking. The sine from 0 to pi is right there, and you keep going, and it's going to be underneath. And if you look at 0 to pi, the average rate of change from 0 to pi right here is 0, and at y is equal to 1, that's the equation of the tangent line we just found, so that the average is on the bottom, the instantaneous is up top, and they both have the same exact slope. All right, for number 6, we needed to make a change to this problem here, so I'll reread it. You are filling a balloon with air at a rate of 5 cubic centimeters per second. When the radius is 3, find the rate, and here is our change. It needs to be find the rate at which the radius is changing. Find the rate of change in the radius. So we have a balloon filling at 5 centimeters per second cubed. Find the rate of change of the radius when the actual radius is 3. They give you a formula. So this is a related rates problem. We should derive both sides. So this is dv dt is equal to, and we take the derivative on the right, the 3 comes over, so that'd be 12 over 3, and 12 over 3 is 4 pi r squared, and we were deriving an r, so it's going to be dr dt. So now we look at what information do we know. The balloon fills at, that's the rate of change for the volume. That right there is our dv dt. So 5 is equal to 4 pi, what else do we know here? The radius is 3. They could give you the diameter, in which case you'd cut it in half, but the radius is 3. 3 squared is 9. If we plug that in here, 3 squared is 9. And I'm trying to find dr dt. So 9 times 4 is 36. So 5 is equal to 36 pi dr dt. And I'm looking for dr dt, so I should divide both sides by 36 pi. 5 over 36 pi is equal to dr dt. Moving on, if we look at 7, 8, and 9, they're right here. So we need some rules for each of these. For the first one, it's an exponential. So it's something raised to a power. So my rule is rewrite the problem, natural log the base, derive the power. So let's start by rewriting the problem. So this is y prime is equal to 2 sine, I wrote that bad, let's try again. 2 raised to the sine 3x times the natural log of the base, so natural log of 2, and we want to derive the power. The derivative of sine 3x is going to be, how do we do a trig function? It's trig prime, keep the angle, derive the angle. So cosine 3x, 3, better answer, 3 cosine 3x. Final answer, 2 raised to the sine 3x, with me rewriting the problem, natural log the base, so ln 2, and then you derive the power, and the derivative of sine 3x is 3 cosine 3x. When we do a logarithm, we need a formula. Our formula, we'll put it right here, is, so this is your base down here, the 2, and this is what we refer to as the stuff kind of up top here. Your derivative, y prime, the blueprint for it is 1 over the natural log of the base times stuff prime over stuff. In this particular problem, our stuff is sine x. So to do this, we're going to say, in the problem up here, it would be y prime is equal to 1 over the natural log of 2 times, and then the derivative of my stuff here, so stuff prime sine would go to cosine over the original is sine. Better answer here, what could we do? We can say cosine over sine is really cotangent. So this is equal to 1 over the natural log of 2 times cotangent x. Better answer, cotangent x over the natural log of 2 is your derivative. For the third one, e raised to something. To find an e derivative, it's rewrite everything and then derive the power. Now you can think of e as the same thing as this one, but when you do natural log the base, natural log of e is just 1, so we kind of leave that step out. So when you're doing e raised to something, it's going to be rewrite it. So y prime is equal to e to the x times, now we want the derivative of x, the square root of x. So I go off to the side and I say, how do I take the square root of x? Well, if y was equal to the square root of x, that's really x to the 1/2. So when I derive that, y prime would be what? 1/2 x to the negative 1/2. So 1 over 2 square root of x. So 1 over 2 square root of x. How did we get this? Rewrite the problem, derive the power. Square root of x, when you derive it, as we showed down here, is 1 over 2 square roots of x. So this is a pretty good answer. Better answer would be this e to the x is kind of up top if you put it over 1, right? So better answer would be e to the square root of x over 2 root x.